If you have gone through the last lecture and tried the exercise, you now know that numerical differentiation contains error. In fact, three different ways we have defined numerical differentiations, and all of them contain different errors. So now in this lecture, we will have some idea that how to control and how to quantify such error. So recall our discussion for numerical differentiation of ux. We defined three different types of numerical differentiations: forward difference, backward difference, and central difference. To understand the errors associated with them, we express ui plus 1 and u minus 1 in Taylor series. So ui plus 1 equals u at xi plus delta x, and if we express it in terms of Taylor series, then it becomes u at xi plus delta x, u prime xi plus delta x square by 2 factorial u double prime xi, etc. And we can write this as ui plus 1 equals ui plus delta x ui prime plus delta x square by 2 ui double prime, etc. We can now prepare an expression for ui prime as ui prime equals ui plus 1 minus ui divided by delta x minus delta x by 2 ui double prime, etc. So we can see that ui prime is in left hand side, and in right hand side we have ui plus 1 minus ui divided by delta x. This is the expression comes from forward difference. So in numerical derivative we have written ui prime equals ui plus 1 minus ui by delta x, but now from Taylor series expansion we can see that numerical derivative is this forward difference expression plus something. This something is what we call truncation error. This error is coming because we are truncating the Taylor series. That is why we call it truncation error. And this truncation error starts from delta x by 2 ui double prime, then delta x square by 6 ui triple prime, etc. So there will be many more terms in truncation error, but we hope that this delta x by 2 ui double prime will be the dominating term. Why? Because delta x is usually small. So as we power it up, then the subsequent terms will be smaller and smaller. The largest term will be probably delta x by 2 ui double prime. So we write it as big O within bracket delta x. This big O is called order. So we call that the order of truncation error is delta x. That means this forward difference is a first order accurate scheme. If the order of truncation error is delta x square, then we call it the second order. If it is delta x cube, we call it the third order. That is how we specify the accuracy of a scheme. When we say that this is first order or second order, we really don't have a means to specify the error, but we have the idea that in a first order scheme like this forward difference, the truncation error will reduce roughly linearly with the grid size. It is not exactly proportional, but somewhat it is related to the truncation error is related to delta x. Similar procedure we can apply for backward difference. Here ui minus 1 is equal to ui minus delta x ui prime plus delta x square by 2 ui double prime, etc. And then I can take ui prime on left hand side, and then ui prime equals ui minus 1 by delta x plus certain terms. These certain terms are extra. You can see that ui minus 1 by delta x is the backward difference expression of numerical derivative. So we have certain extra term, and this extra term is the truncation error in backward difference. we find that the first term, that is delta x by 2 ui double prime, and we hope that this will be the dominating term in truncation error. So in a sense, that truncation error has the order of delta x, and thus backward difference is also, just like the forward difference, is a first order accurate scheme. So the error will roughly reduce with the grid size delta x. Please note that backward difference and forward difference for a given function may not have exactly the same error, but they are of same order. That means the error will reduce with grid size in sort of similar manner. Now we come to central difference. In central difference, we expand in Taylor series both ui plus 1 and ui minus 1, the way we already did, and then we take ui plus 1 minus ui minus 1, then we have twice delta x ui double prime plus delta x cube by 3 ui triple prime, etc. You can see that ui double prime is cancelled out. So we can write ui prime as ui plus 1 minus ui minus 1 divided by twice delta x minus delta x square by 6 ui triple prime plus additional terms. So if we compare this with central difference, we see that the first term is delta x square by 6 ui triple prime, and then there are additional terms. All these terms are truncation errors, and thus the truncation error in this case has an order of delta x square. So here we see that central difference is second order accurate scheme, unlike the forward and backward difference, which are first order accurate scheme. So here, if we reduce the grid size, the error in central difference will reduce very fast. So please note that when we are comparing a first order scheme with a second order scheme, we don't mean that error in the first order scheme will be higher than the second order scheme. We don't know that until we got the exact value. But we can say for sure that if we reduce the grid size, that error in the second order scheme will drop much faster than error in the first order scheme. So when we go for very small grid size, it's quite likely that a second order scheme will give me more accurate estimation of numerical differentiation. Now we'll end this discussion with a small exercise. I have given here a test function x square plus 2x, and then what you have to do, you compute derivative using forward difference, backward difference and central difference scheme for different grid size, and then you plot error versus grid size for all three schemes. You select your grid size judiciously so that we can have a feel, we can see that how the errors will vary with grid size. Now we really don't know how to calculate truncation error, we only know the order. So how you will plot error? So in this case, what you do, you simply take the difference between analytical and numerical derivative as error. This is not exactly truncation error, this is truncation error plus other things, but let's not focus on those details right now. We'll discuss more about errors later. So right now you simply carry out this exercise, write a small program to create the data file, and then plot the data file using the plot software of your choice. That's all for this lecture. Thank you very much. I'll see you in next lecture.